Mhm. Hello, dear guests. Thank you for joining us today. This is Master of Computer Vision program, and we continue the series of our industrial webinars. And today we have special guest, Aleksandr, with very interesting report or presentation. So, Aleksandr, you're welcome.
Thank you very much for your kind introduction. Can I share the screen?
Yes, you may.
Okay. Oh, nice.
Yeah, it works.
Can you see the whole screen right now? Okay. Okay, let me start. Thank you, dear listeners, for inviting me. Today, I'm going to talk a little bit about, first of all, basics of autonomous driving. In order to introduce the domain, the difficulties of tasks that we are trying to solve. And then probably I'll show a little bit about perception, but mostly about behavior tasks. Anyway, I guess it could be interesting, at least, for example, to look into the very different domain in comparison to what you're doing on an everyday basis. Yeah, let's start. The presentation title is Autonomous Driving from Basics to Behavior Challenges. My name is Alex. Okay. First of all, would like to say that it's not only and probably not only my job. That's only has been done in collaboration with my colleagues, Wei, Jonathan, Nation, Lat, and Jen Lee, and much more different people that we are working on in Nuro. So let's go. The content is quite diverse. We can start with the introduction, then move into motivation slides, then look into two different aspects of how we apply recent state-of-the-art approaches inside behavior. It's mostly diffusion and RL. Look into a couple of examples, and then go to implementation conclusions. Anyway, I am not sure probably that we would have the time to cover everything here, but can I ask for moderator to notify me like 5 minutes before the end time?
Okay, sure.
Thank you. Okay, let's go with introduction. The first question would be, who is the speaker? And probably don't know me, and probably even not probably, and just definitely you don't know me. My name is Alex, as I said. Right now I'm working in Nuro. Nuro is a self-driving company. It's still a startup, but it's quite big startup. It's about 1,000 of employees. But here the slide is mostly about that I'm not working only in the industry, and at the same time I'm not we're working only inside academia. I'm trying to combine both because this is, from my point of view, the most beneficial way to, first of all, grasp state-of-the-art approaches, but at the same time to understand how to apply all these approaches, how to say, for practical tasks, for real life. And previously I worked in LSI, Huawei, Artificial Intelligence Research Institute in Russia. Right now I'm in California. And at the same time, I have a PhD in very theoretical domain, theoretical computer science. Yeah, and also right now I'm having some lectures on the theory of deep learning in MIT, Lomonosov, Moscow State University, and right now I'm studying in Sofia University here in California as well. Yeah, and my motto is standing on the shoulders of giants. It means that sometimes you can be, you can think that you are really cool, but it's not usually, just because usually you use the achievements from your colleagues, from the all the previous cool papers in the literature. Okay, let's move to the area of autonomous driving. Let's start with the definition. Definitions, usually we have two definitions. It's abbreviation AD and SDV. AD is autonomous driving, and it means basically the task itself. And SDV is a self-driving vehicle, the car where we install all the, I don't know, self-driving capabilities. And self-driving is one of the most and one of the difficult tasks because it comprises usually all the state-of-the-art achievements for all this current computer science activities. It's computer vision, it's behavior, it's control theory, it's decision theory, sensors, materials, and more. That's why it's, probably suggest, yes, and recommend for anybody at least to try to understand the, how to say, different tasks inside autonomous driving, because it doesn't matter from which specific area of expertise you are, you can work inside autonomous driving, you can find the place. It could be either perception, behavior, any other field. It doesn't matter whether you're a software engineer or hardware engineer as well. And the main, how to say, complexity which visible for external viewer, usually it is connected with safety. And safety of the DV and other agents on the road is very crucial to the whole autonomy. And when we're talking about a stack of technologies, we can really say that we have inside autonomy the stack, and to the right you can see the brief explanation. So we are starting from the inputs, and we go to perception, prediction, and planning. Usually this perception, prediction, and planning are called P3 or P cubed. They are the main software parts if you're talking about software. But we also have hardware parts. It could be sensors at the input. We also need to take care about controls, steering wheel, acceleration, like wheel and pedal inside the car. And at the same time, we need to understand the map around. Sometimes we can use a so-called high definition map, and this is our helper. This HD map contains information about the road. So let's look a little bit more about this stack itself. We are starting with the sensors, and sensors are eyes, ears, nose, and etc. of the car. And you can see here that there are multiple different sensors, and the application and the reasoning about it, that every sensor grasps a little bit different, I don't know, area of field, longevity, or I don't know, distance to the objects. So we can use ultrasound, LiDAR, camera, radar, and all of them are designed to grasp very different distances, and they have their pros and cons. At the same time, we also need to rely much on the usual RGB information, RGB cameras, and usually a lot RGB cameras around the car. It could be like 5, 10 or something. And the problem here is very obvious, is how to synchronize all this information, because it's so we need to think about how to deal with this multimodal information, how to fuse it in an efficient and effective way. At the same time, it's expensive. More sensor you have, the more expensive your car. Sometimes the how to say, the cost of the sensors inside the self-driving car can be comparable with the cost of the car itself. When we're talking about HD map is a very cool thing. It contains some information about the road, like lanes, crosswalks, traffic lights, etc. The problem is that every company has its own format. There is no well-established format for HD map. For example, Waymo has its own format, Argo AI has its own format, Nuro has its own format. Everyone has its own format. And it can be also sort of significant overhead how we're trying to get this HD map because you need to run some specific vehicles and grasps all this information around at different places, different locations, because this information much more fine-grained in comparison to, for example, Google Maps or OpenStreetMaps. And that's why it's quite costly. Okay, then we are going to perception, and probably this is much more common to you. And inside the perception, two main subtasks. The first one is detection. And additionally, like segmentation, depth estimation, they are all combined into the one big part, which is called detection. And we need to detect the objects around. Cars, I don't know, traffic lights, intersections, pedestrians, other agents on the road. The problem is quite unusual, but very difficult. We need to deal with the long tail. These are usually small and unusual objects on the road and some anomalies, because you can never in advance understand what different type of objects can be on the road. They so it doesn't matter how you can be design in advance the number of different classes and types of objects on the road. When you're trying to deploy your car, like almost every day, there could be some very specific object that doesn't belong to any class that you designed in advance. That's a problem. And then the second subtasks, this is when we have all the detections. So we need to combine all the different objects on different frames into one continuous trajectory. And this is what we call tracking. We need, how to say, to stick them together into one continuous track and to estimate their coordinates in order then to feed into the prediction part. Problems, this track association is not simple problem, and we need to do this flickering object because at some frame we can see some object, and another frame this object can be, I don't know, occluded by some others, or we have some perception problem. For example, it could be this object could be very small, and the perception model can just lose the attention to it. So that's the problem. Then we go to the prediction. And when we're talking about prediction, this is the task when we need to, I don't know, hypothesize about how other objects on the road can behave in the next second, in the next 5 seconds. Usually this horizon is not so big. I don't think that it should be more than 10 seconds. Yeah, but for sure, how to say, the longer horizon, the better, but at the same time, it should be much and would be much more unreliable and uncertain. So here we are trying to provide multiple possible trajectories because we don't know the reasoning inside the heads of different agents. We can only hypothesize the reasoning about the intentions. Yes, some problems here. We need to deal with multimodality. So as you can see here, multiple errors. That's why we need to hypothesize that every object on the road can drive either, for example, straight or turn to the right or have this lane change. That's the thing. And the second one, this is tightly coupled with prediction, and sometimes we can deal with the combined prediction and planning models. And essentially, this is the planning of your own vehicles, of your SDV vehicle, or usually it's called EGO. And we are planning this SDV future based on the predictions of agents around. At the same time, we have our route in advance. For example, we are going to move from point A to point B. Yeah, problem here is we need to be consistent in terms of other predictions. So you can see here the two different futures, and future 1 and future 2 are consistent. So if Ego goes straight, 2 other agents are just waiting for him. But if ego waits for them, yields, so two other agents can go first and only after SDV moves. Then we're going to the last part, it's control. So here we need to realize and control with the actions based on motion plan. And motion plan, this is what we have from planning model. And here we need to deal with steering control, with acceleration, etc. Problems, the problem is that we could have some dynamic and kinematic limitations. For example, not every trajectory which comes out of planning can be physically plausible, can be physically realizable, because you cannot like turn on 180 degrees at one second, etc. And yeah, and inside Nuro we have the whole autonomy stack. We are researching every part of it, and let me click and show the link, the video source. This is, let us look only in 1 second. Let me skip and go into perception, because I think we are mostly interested here in the perception. Let me by the way, can you hear the voice or not?
I'm not.
Okay, let me just, there is something needs to be, this is when I'm sharing, I need to change something. Share sound. Can you hear right now?
For me, still doesn't work.
Okay, but strange that I cannot see as well right now, so something strange. Okay, but anyway, let us look. So let me just go back. So it's basically our head of software, Albert, is talking about how different sources of sensors do we use. We are using LiDARs, radars, etc., etc. You can see. So the first type of information could be LiDAR, like we are using inside our ML and how we deal with geometry. Then also LiDAR, and at the bottom, at the up, we have RGB cameras. We're also using radars with a nearby object, multi-surface tracking, and here the parking lot. And I would say that parking lots are one of the hardest areas, just because the number of anomalies on the parking lots is really big. Just 1 minute. So you can see like the complexity of the task. So you need to operate not only during the day, but during the night as well. And during the night, during the fog, or during such hot conditions, sometimes RGB cameras are not so cool. Yeah, I think that's could be okay. So, and that's why you need to rely sometimes on different sources and modalities of input information, like LiDARs or radars or etc. Okay, let me continue. Yeah, and I have, I think, 20 or 25 minutes. Let me go very briefly for the behavior part. So I'm behavior guy right now, and I'm really sorry for providing very short introduction to the perception, but I guess it would be interesting. And so the problem is that to do so we need trustworthy prediction for other agents. Recall this autonomy stack and the prediction part. And we need it for both predictions and simulation, because we also need to evaluate our system, and that's why we have our own simulator. At the same time, we would like to have the flexible and safe selection. Selection means that usually the autonomy stack, the planning model, provides, I don't know, multiple sources of plans. They are basically multiple trajectories, possible trajectories for ego vehicle. And we need to choose, we need to select which motion plan to use. And there are multiple ways how to do it. And sometimes these plans from out of ML models, sometimes they are out of heuristic models, sometimes there could be some contingency plans, etc., etc. And we need to deal with it. We need to deal with the number of trajectories, like as could be 5, 10, 15, or something. And our approach is like to have it better training, evaluation, and reasoning, which really leads to safer driving. When we're talking about better agents prediction simulation, the problem is that when we usually used of imitation learning prediction model for other agents, it could lead to unreasonable proposals because of distribution shift. And the distribution shift is really hard problem for autonomy, because when you're trying to train either on simulation or on the on-road logs that are captured by different, for example, vehicles before you start to train, doesn't matter. On like the next day, the situation will be different. Different to what you previously recorded, and different in comparison to what you can simulate in your simulator. So that's the case. And the historical approach is to use only heuristic-based agents. What we propose a prediction model to design in such a way so it could lead to better distribution coverage and recall. So we could use it for both simulation and agent prediction. And when we're talking about selection, the problem is that for autonomous driving, some decisions have long-term and delayed consequences, like deferred actions, like occluded agents on the road. So we need to hypothesize sometimes, and need to roll out the future. This is the problem. And historical approach is to use long-term predictions. When we talked about a little bit about this prediction, I have said that we could use from 1 second to 10-second predictions. So long-term predictions could be like 10-second predictions, but they're super unreliable, and we have a big variance in terms of these long-term predictions. The better solution here is to learn a model that takes into account expectation over all futures. And the selection is just to narrow down the search space. Okay, diffusion models. I think probably most of you or all of you just know what are diffusion models. About their success, yes, diffusion model is a generative model. Basically speaking, Markovian hierarchical variational autoencoder. This is what we are using. This this is our analogy. And diffusion is just adding step-by-step some portion of noise, and we have forward diffusion process, encoding, and the reverse diffusion process is decoding. And right now, I think everybody of you just know all the success of diffusion models, like Imagen, OpenAI, DALL-E 2, Midjourney, and seems like text to image and also text to audio, text to video, and something like this. All this generation has been done. Yeah, but what about other tasks? And much more importantly here, what about autonomous driving tasks? And until now, to the best of my knowledge, we have two main areas of work. One is called controllable traffic generation. This is the paper from NVIDIA, where with the diffusion-based model, we are simulating other agents on the road for traffic. And we also have the paper from Waymo, it's called motion diffuser. This is for joint prediction. And what we are doing inside Nuro, we are trying to combine both these functionalities, prediction and simulation for the one single model. Yeah, our main goal is to develop this trajectory generation model that can really cover the distribution. Because for prediction, the good recall, this is vital. This is what we need in order not to have any safety problems. At the same time, we would like to improve the closed loop simulation. If you don't know, the closed loop simulation is a sort of simulation done step by step when every agent is reactive to any other agent's actions. It's not like open loop simulation. We are just predicting the futures for the 10 steps. And we would like to do it with so-called diffusion-based trajectory generator, or DTG. Yeah. How we are going to achieve it? We are going to use variational diffusion model, VDM, by explicit elbow optimization. And closed loop simulation will provide us more useful signal for RL-based, reinforcement learning-based trainings. Yeah, what are the features? We are learning diverse behaviors. We're providing good NLL. And it's at the end, it leads to stable, consistent, realistic simulation. Yeah, this is the very simple architecture of it. So we have encoder, we have its features. We also have noise, we are concatenated, adding noise level, go into very simple solution with NLP. We are using like energy formulation here, and then just train it. Also note that we can use different encoders. That's also quite important direction of the work. So we need to deal with multiple encoders. Sometimes we are historically changing the like encoder version 2 versus encoder version 3. Sometimes we can even use multiple encoders in parallel. Some of them more suited for behavior, some of them more suited for perception. For example, we can use perception encoded information. Yeah, and about DTG, the first task was like to ensure good so-called mean ADE. What does it mean? ADE is average displacement error. This is L2 distance between trajectory points. And when we use this diffusion-based model, usually it provides a multiple trajectories. This is just a generative model. We're just sampling, and you can see here the green one, different predictions. They are just a number. And blue one is a map, red one is ground truth future, and the dashed, I don't think we can see it, but anyway, the history. But how to deal with this sampling-based approach? So we are doing sort of post-processing by clusterization. After we sample, say 100 of features, we then clusterize them into 6 or 10 or 5 clusters, basically speaking, into a small number of clusters, and then we can even calculate the probability as the size of this cluster. The more number of trajectories inside the cluster we have, the bigger probability this cluster we can assign. And for example, we are after moving from 128 to the number of 6 trajectories, you can see here. So you can decrease all these dense trajectories into quite reasonable ones. So where we have like going straight and going to turn to the right or to the left, or here this very tricky object. This is pedestrian, and it's quite uncertain. But anyway, here we can see quite reasonable trajectories. The second part is about deep RL. Let me go quickly here. Okay, so this is the overall pipeline for RL. So we have simulation, we have policy, we have here the feedback loop, and for this optimized stage, we would like to optimize the weights by some algorithm. This is DPRL. So we would like to maximize our reward under the policy while limiting probability of risky event. What we are going to learn, we are going to learn state action Q value function. And what we optimize, we iteratively improve Q function for all states and actions. S here denotes stage, and A denotes action. Yeah, this is how we can look into long-term goals, how to update all this information. But let's go to the motion selection. Motion selection. Yes, as I've said, the task is to select between discrete number of trajectories and a very definite number of trajectories. So we are ranking trajectories rather than producing. But low-level trajectory generation can be well handled by different trajectory generation models. It could be, for example, DTG. And we call this motion selection RLMS, array for motion selection. As you can guess, no, we are not so good in naming, so it just functional names for both RLMS and for DTG. Yeah. And why it is important? So why we are not producing trajectories and just selecting them? It allows heuristics and domain knowledge to filter the trajectory space for RL. Yeah, basic RL, we have state encoding, action encoding, we have policy and values. For value, we have these trajectory Q values. For policies, we have trajectory probabilities. And actions here are trajectories. Yeah, Q values just dense rewards. We have a number of them, reward 1, 2, 3, etc. Problem is no concrete notion or constraint on safety. For this specific need, we are adding the risk. And this, so we would have the Q risk values for it. And risk values are also sparse rewards, risk 1, risk 2, risk 3. But we still do not have the hard constraint on safety. And for this specific direction, we are adding additional policies, which are called recovery policy. And again, these are trajectory probabilities. So as you can see here, we have 2 sets of Q values and 2 sets of trajectory policies. And this is so-called constraint RL. So we have the Q risk values, if it is safe or not. If it is safe, so we are using usual policy. But if it's not, we are going to invoke failover policy. And this is during the inference. And as a whole, this framework is called recovery RL. One of the inventors of this recovery RL, Ashwin, is right now working inside our group. And so you can see the very brief, I don't know, illustration of it. So we have the maze, we have the policy P, PyTask, and we are sampling the action from it. And then we evaluate whether it's safe or not, and we are evaluated by Q risk value. And if it is safe, so it's less than some threshold, epsilon risk, so we are follow this direction. If it's unsafe, we need to execute the recovery policy. And how it's how to say built. So we have this RLNS policy. We executing current RLNS policy, simulating start trajectories. So for inside replay buffer for off policy algorithm. Then we have the transition. We use them to train to task and risk critics. As we discussed, we have dense rewards and risk values here. And then we are just combining them, just their weighted combination to have the so-called util, task util, and recovery util. And based on it, we can just use the task policy and recovery policy. And then we're combining them just see whether we are better or not than some predefined threshold, and go to RLMS policy as well, again and again and again. So how we are combining all these values? So the final RLMS policy uses a combination of both the task and recovery policies. First, we score all possible actions with each of our risk critics. Here we can see that we have 3 risk critics. Some actions are marked as unsafe, like red. So we have, basically speaking, only 3 safe actions. So we renormalize the task policy and just sample from these first 3 items. But when at least for every action, if at least at one risk values we have the unsafe action, so and we can see that we have for every row we have at least one cell red, so we need to invoke the recovery policy. And for recovery policy, we are not renormalizing anything, we're just sampling from the whole recovery. Yeah, and so that's how we have the whole framework on our plate. It's not so easy, but it's very reasonable, and it's really provide us the methodology to deal with different plans from different sources and really improve the safety on the road. Some examples. First, what I'm going to show is the examples of DTG. So we have the potential right turn, although it is not inside the ground truth. So we can see the ground truth. This is the history, the dashed red one, the bold red ground truth, but DTG provides us reasonable turns to the right and even for the different lanes. And the same here. It can provide go straight and go to the left lane to the left one. It really catches the recall. Again, here we can see the potential left change to the left. So it's going from the right to the left, and ground truth is just go straight. And we have here go straight trajectory. But at the same time, we have trajectory. Please change the lane. The same is for the trajectories on the bottom. And yeah, we also can provide uncertainty for such road users as cyclists or pedestrians. So you can see here, the cyclist is one of the hardest road users because it can be really unpredictable. And so we can see so it can go, and this history is like goes here. And it can go to the left and can go to the right, and we are grasping this uncertainty. And some examples for this RLMS, and here are for closed loop simulations. So you can see here that's OK solution where we will overtake a Nuro on the left, this one. And yeah, we are really making some break and everything is OK. So the top is on road lock and bottom is simulation. The second OK case, this occluded unprotected left turn. And yeah, bottom the simulation, so we can really wait a little bit before every agent just goes, and then we are smoothly transition to the left turn. But not everything is okay. Sometimes we have the problem with stability. This is the nature of the algorithm, because sometimes selection is a combination of different plans. We are just stitch them together. And because we don't have a single initial good source of to choose from. That's why this, I don't know, stick together plan can be a little bit flickering. And that's why you can see here we are yielding too much before go. For example, on the road, we already somewhere very far away, and because of all this flickering, we are a little bit conservative and moving not so fast, I would say. Limitations. DTG, for this diffusion-based trajectory limitation, this is what is inherently presented for all diffusion models, that this is sampling only inference. It's, to be honest, hard to use in the production. You need to distill the models, or you need to work with this trade-off between performance and latency. because it's consecutive predictions. Yeah, latency to performance trade-off, and non-deterministic simulation because you need to sample. Yes, you can fix, I don't know, random seed, but I wouldn't say that it's the best way to do. For RLMS limitation, there is still do not have hard constraint. To be honest, we have it, but how to define this, how to, I don't know, to map this epsilon threshold with the real life, this is the question, it's still the ongoing work. Yeah, still rare sparse event, it's very hard to learn, like collisions. And it's sample inefficient because it takes many simulation steps to learn, but I think it is the, I don't know, the nature of RL. It's not only for autonomous driving itself, it's for any RL algorithm we have the same problem. For conclusion, diffusion-based models help to match the distributions and not points. That is very important. That's why we really like this approach, because we can grasp even, how to say, long-term events, but they could just have low probability. So we need just to sample more in order to get these long-term events. Learning selection provides long horizon reasoning. This is our RLMS where it helps us. And funny note here that really academic state-of-the-art approaches can be used for practical tasks to add more safety. They really work, and we really can use them. And which is a little bit funny then that, for example, our approaches for DTG has been designed, I don't know, even 1 year ago, and we started to work on it. Yeah, and only after that we have seen these new papers from Waymo and from NVIDIA, which basically using quite similar what we are doing. So it seems like we have so-called external confirmation that we are doing the right thing. Yeah, and just use some useful links. I think we can share the presentation afterwards, and I have used multiple sources. Yeah, and probably some sources much more, I don't know, detailed information can be found. So it's I've done some lectures for some Mountain View high schools, also some presentations for BDDs, Berkeley Deep Drive and Berkeley AI Research Lab, the previous and this year. Also this CVPR, I've done this presentation about RLMS and DTG. And also the last but not the least here, link for you on YouTube. We are holding the so-called Nuro Tech Talk series, and multiple bright PhDs and scientists throughout the world just presenting their talk there, mostly about autonomy, but not only. And I would encourage you to look at least to look at it. Probably you could find somebody interesting to you. And yep, thanks for listening. I hope I'm on time. And now I think we could talk, and you can ask any questions, and I can answer them in Russian.
Так, дорогие гости, если у вас есть вопросы, пожалуйста, you're welcome. У меня так они точно есть, но сначала я дам шанс нашим гостям. Пожалуйста, можно писать в чат, можно поднять руку и голосом задать. Пока все думают, у меня будет вопрос такого потребительского, скажем так, уровня. Правильно ли я поняла, что такое решение вот этого беспилотного вождения может быть встроено в любой автомобиль, при условии, что если у меня есть достаточное количество денег, и я закуплю нужное оборудование?
Да и нет. Есть разные компании, которые делают разного рода решения. Это очень хороший, кстати, вопрос. Есть компании, которые предоставляют так называемый комплект компактное решение, которое заключается в виде простой камеры, которая на основе этой простой камеры будет помогать вам делать решение. Она подключается к CAN-бас в машине, ее можно подключить, и она будет вашим помощником. То есть там уже в эту камеру и в небольшой вычислительный модуль встроено все, как бы и perception, и prediction, и planning, и controls, то есть через машина будет управлять вашими рулем и там нажатием на педали газа. Но нужно понимать, что эти решения, они вообще не очень хорошие в плане сложных ситуаций на дороге. То есть они очень хорошо будут вам помогать, когда простые ситуации, когда вы едете по шоссе, когда много места. Это такой улучшенный помощник. Но как только делают, то вообще как бы вся борьба между там, ведущими компаниями self-driving заключается в том, чтобы лучше заниматься, лучше обрабатывать случаи, которые называются long tail, вот этот длинный хвост. То есть чем более нестандартная и сложная ситуация, тем больше видны огрехи и проблемы, пробелы в вот это, в беспилотном стеке. Поэтому да, можно такие, они такие решения даже есть на рынке, я даже не могу, не скажу, как они называются, но они есть. Вот, но при этом ведущие компании так стараются не делать. Вот, они стараются выпускать, то есть полно, как сказать, вот это все решение, они обвешивают еще машину всеми необходимыми датчиками, потому что у них получается полный контроль за тем, что они могут видеть, устанавливают кучу так называемых вычислительных мощностей, там видеокарты, которые работают на борту, которых их целый ряд, там, которые обрабатывают разные модальности информации. Вот, поэтому, например, у нас есть свой бот, и он примерно, вот сейчас я покажу, вот он примерно вот ровно так и выглядит. Вот это ботики такие Nuro, они очень симпатичные, и там нет водителей, это просто боты доставки. Кстати, даже не рассказал, собственно, что такое Nuro, да, извиняюсь. Nuro – это компания, которая вот делает такие симпатичные боты, которые занимаются доставкой груза. Поэтому там внутри никого нет, они доставляют пиццу какую-нибудь из машин, какую-нибудь, я не знаю, продукты. Там есть холодильник, они могут, то есть можно продукты, которые требуют заморозки, можно доставить, можно обычные продукты, там какую-нибудь Кока-Колу привозить. Вот. А есть еще одно направление роботакси. То есть роботакси – это Круз, Waymo, которые на дорогах Сан-Франциско ездят. Там уже они людей возят. Поэтому у нас задача немного проще. Нам не нужно заботиться о комфорте людей внутри. То есть мы можем себе позволить чуть больше с одной стороны, но и чуть там есть свои особенности. Да, поэтому еще раз прошу прощения за длинный ответ. Кратко, но отвечая на ваш вопрос, есть решение, которое позволит встроить в любую машину, ну, даже современную машину, какое-то стороннее решение, подключить CAN-бас к шине данных. А есть решения, которые заточены на то, что они будут использовать свои машины, ну, либо там чужие машины, но все равно они будут обвешаны своими датчиками, будет поставлено внутри там какое-то количество обрабатывающих мощностей, и поэтому так просто и уже не встроить к себе в машину.
То есть у вас больше это B2B, да, решения? Какие-то крупные
Да,
супермаркеты
да,
закупают?
да, именно так.
Мгм.
То есть рассчитано на то, что супермаркеты, службы доставки и тому подобное будут как раз и сотрудничать с нами. Вот именно такие бизнес, да, не кастомеры,
Мгм.
не клиенты.
Очень интересно. Спасибо. Это был мой первый вопрос. У кого-то из гостей появились, если вопросы, то я могу вас пропустить вперед. Там был вопрос, где вы работаете, но вы уже ответили достаточно подробно, с очень очаровательным автомобильчиком. Тогда я задам свой второй вопрос. Я не очень успела понять, какое ваше решение, когда вы говорили про вот predictions. То есть вы сказали, там был какое-то стандартное, там historic что-то decision, и вот ваше. Можно еще вкратце на русском, что у вас за решение?
Давайте. Да, я сразу могу сказать, что извиняюсь, знаете, тут как-то русский забыл, а английский еще не выучил, поэтому вполне может быть, что я непонятно выражаюсь. Да, решение следующее. Решение у нас на основе диффузионных моделей. Диффузионные модели – такие генеративные модели, которые на основе достаточно продвинутой теории пытаются схватить распределение данных, на которых ты обучаешься, и потом сэмплировать очень похожие данные из этого распределения. Более того, там есть оценки, и чем хороши диффузионные модели, что там есть оценки на NLL, Network Likelihood, то есть они действительно оптимизируют вот это самое распределение, в отличие от тех же самых ганов, например, в которых мы можем только догадываться, как там все получится. И вот это вот решение, оно на основе входных данных, то есть на основе исторических, ну, сейчас вот покажу. Тут плохо видно, кстати, мне вот вторая картинка больше нравится, вот здесь. Вот, на основе входных данных, это данные о карте, то есть это данные о перекрестках, данные там о линиях и бордюрах, о истории агентов на дороге. То есть здесь мы видим сразу 3 агента едут. То есть 2 направо и 1 налево, если мы говорим про lane change, про правую верхнюю картинку. То есть вот оно поступает информация о карте, поступает информация о вот этих вот пунктирных линиях, то есть об истории машинах на дороге. Нам нужно предсказывать будущие траектории машин. Вот предсказания — это зелененькие, вот то, что они в будущем. То есть мы как сэмплируем какое-то количество, например, 100 штук, например, или 16, там зависит от решения. Да, вот здесь можно лучше показать, да. Получаем такие очень плотные пучки, потом мы их кластеризуем и получаем уже то количество, которое нам нужно согласно каких-то требований. Вот здесь, например, нам нужно 6. У нас 6 разных предсказаний. Они могут быть все равно очень похожи, они могут быть разные. Например, кто-то поворачивает направо и одновременно едет вперед. Мы не знаем, мы не уверены. И затем мы передаем это в модуль принятия решений. То есть модуль планирования, точнее. А планирование то есть это все лишь информация о агентах вокруг. То есть мы едем по дороге, мы смотрим вокруг, думаем, ага, как поедут другие люди в течение 3 секунд. После чего мы пытаемся предсказать. И на основе этого предсказания уже прокладываем наш собственный путь. Чтобы не знать, точно так же, как мы действуем на дороге сами. То есть мы примерно прикидываем в каждый момент времени, как другие едут, и пытаемся одновременно, имея наш собственный план, куда нам нужно доехать, там грубый, примерно, и одновременно пытаемся не знаю, не пересечься ни с кем на дороге, ни в кого не врезаться. Вот этим занимается модуль планирования, то есть который на основе предсказаний и исходного грубого плана пытается сделать очень детальный план, как, не знаю, машину проложить так, чтобы удовлетворить всем ограничениям.
Ну, стало понятнее чуть, но понятнее. Вопрос у Николая Руденко, если он еще готов,
Да,
то,
добрый день. Да, простите, я по-русски тоже задам.
конечно.
И тоже извиняюсь, потому что я, к счастью или к сожалению, не инженер и не компьютер-сайентист, я социолог. Вот, но я тоже изучаю беспилотные автомобили, они мне интересны. И вот позвольте мне вопрос тоже немножко своей сферы. Он касается того, о чем вы тоже сказали. У меня 2 вопроса. Первый вопрос. Как происходит вот такая научная коммуникация между компаниями, потому что меня, наверное, удивило, что вы говорили, что вот вы опирались на работу там кого-то из Вейма, других компаний, и потом они на ваши работы опирались. Просто интересно, это происходит через научные статьи или как-то еще? Вот, как происходит такой обмен? И второй вопрос, просто по вашему ощущению, кто из компаний, не обязательно беспилотных автомобилей или вокруг них, например, там Bosch и других, кто такой самый плодовитый в научном плане? Вот, именно из
Хорошо,
коммерческих компаний. Спасибо большое,
хорошо.
Александр.
Спасибо, да, очень хорошие вопросы. Начну со второго. Наиболее плодовитая компания Waymo. Она, к сожалению, ну, я не знаю, к сожалению или к счастью, пока вот жил в России, я практически не слышал про нее ничего, вот, но на самом деле это самая, как вы правильно заметили, плодовитая в научном плане компания, потому что там хороший большой research отдел, и они приличны по количеству людей, они могут себе позволить пускать часть времени своих сотрудников на исследования, публикации статей. Далеко не все компании могут себе позволить. И, ну, как кажется, сейчас именно с точки зрения научного ландшафта, именно они, то есть компания Waymo это компания, отколовшаяся в свое время от Google. И до сих пор Google их спонсирует, собственно. Это часть Google X, так называемая. Ну, кстати, наши 2 фаундера из Nuro, они тоже оттуда, из Google X, они свой собственный стартап организовали. Вот. То есть я бы посоветовал смотреть на работы Waymo, и пишется Way и не море, а MO. Просто Waymo. Сейчас напишу. Так. Вот эта компания считается именно наиболее плодовитой в научном плане. Как происходит обмен? Обмен через научные конференции. То есть понятно, что есть какие-то там неформальные разговоры между сотрудниками, вот, и, ну, по большему счету, многие компании очень делают похожие вещи, кто-то чуть-чуть раньше, кто-то чуть-чуть позже. Почему? Потому что здесь вот в Силиконовой долине, вот тут Кремниевой долине так устроено, что, короче, все, ну, очень много инженеров прыгают просто между этими компаниями, тут нет никаких запретов на там 3 года не работать в компании-конкуренте, такого нету. Вот, все просто прыгают между этими компаниями, и, естественно, как бы они хоть и не уносят код никакой, но решение в голове у всех примерно одинаковое. Поэтому примерно все про все про всех знают, так вот неформально говоря. Просто где-то часто очень решает данные, которые ты собираешь. Потому что данные очень важны, потому что у кого есть больше мощностей эти данные обрабатывать, у кого есть больше мощностей данные собирать, тот и в фаворе. Вот. Ну, как-то так.
Спасибо большое.
Пожалуйста. Есть ли еще какие-то вопросы? Я думаю, у нас еще есть 4 минуты. Я бы с удовольствием ответил на какой-нибудь еще, не знаю, может быть, вопрос по технологиям, но, наверное, из-за того, что я не из perception мира, хотя в свое время работал в компьютерном зрении на лет 8, потом переключился, наверное, года 3 назад, поэтому вот про perception очень мало.
У меня есть маленький вопрос от наших студентов текущих, кто у
Мгм.
нас уже учится. Они не могут технически что-то тут написать, попросили его задать. Если вот он еще студент, он занимается компьютерным зрением и интересуется вот этой темой, но не включен ни в какой большой там стартап и вообще компанию, с каких бы небольших там вот как раз технологических решений начать свой путь вот в этом беспилотном мире? Понятно, о чем я спросила? Я сама, насколько понимаю
Решений,
вопрос. Ну,
решений.
ну, каких-то
Ну,
задач, которые вот можно начать решать, локальные.
ну, задач можно, да, то есть,
Да, наверное, не решение, задач. Мгм.
да, потому что то есть компания предоставляет уже решение.
Да.
На основе одного человека сделать что-то сложно. Я думаю, имеет смысл посмотреть в челлендже. Большое количество челленджей, ну, не то, что большое, но не один. А порядка, может быть, 3-5 каждый год челленджей в Autonomy Driving происходит в мире. Например, Waymo Open Motion Dataset Challenge, я думаю, New Plan, там, New Scenes. Короче, я бы посоветовал, почему посмотреть в открытые челленджи, которые устраивают ведущие компании, потому что у них хорошо определен, входы, выходы, метрики, ничего про это думать не нужно. То есть ты просто пытаешься заоптимизировать какую-то модель. И там есть как perception-based, так и behavior-based. То есть где-то нужно обращать внимание на предикции, где-то нужно обращать внимание на как обрабатывать сенсорную информацию. То есть даже в рамках одного челленджа могут быть разные треки. Там больше с уклоном на компьютерное зрение, где-то больше с уклоном на поведенческое планирование. Вот. То есть вот с этого можно начинать. То есть так обычно и получается, что в университетах люди начинают как раз с челленджей, и если у них получается, они выиграют какие-то там первых 3 места, их могут заметить в компаниях, уже пригласить в компанию на стажировку.
Мгм. Мгм. Отличный ответ, очень полезный для наших всех студентов. Мгм. Спасибо. Ну, тогда я думаю, да, мы завершаем как минимум запись.